Hello students, welcome back to A-Star Tuition channel. Today we'll learn about the logarithm along with its graph. We're going to start off with the definition of log and the rules associated with it. Okay, logarithm. Log AX simply means a to the power of something is equal to x. This is the definition of logarithm. Okay. Example, log 2/8 simply means 2 to the power of something is equal to 8. And we all know that this power has to be equal to 3. And therefore, log 2/8 is equal to 3. Okay. Next, the initial constraints of log. Log AX has some initial constraints in which both A and X have to be positive number. In addition to that, A also can't be equal to 1. Okay? The reason why A can't be equal to 1 is because 1 to the power of anything remains 1. Okay? We can't have log 1/5. This simply means 1 to the power of something is equal to 5. 1 to the power of any number always equals to 1. Therefore, there is no number that could actually fit this equation. Yeah. So these three are the initial constraints. Let's move on with the rules of logarithm. The first one is log AX positive log AY is equal to log AX times Y. Assuming that log AX is defined as P and log AY is defined as Q. Okay. According to this definition right here, the log AX here, which is equal to P, could be rewritten as A power P equal to X. While the second one is leading to A power Q equal to Y. Okay, we're going to verify this equation. The left hand side will be equal to P positive Q, while the right hand side will be equal to log A X times Y, which is the product of these two terms, A power P times A power Q. The product of two terms having the same base, different power, will be equal to A power P positive Q. It's the base to the power of the sum of the powers. Okay, going back to this, according to this definition of log, this log A power P positive Q means A power what equal to this, which is equal to P positive Q. Okay, and therefore we have verified this equation. Moving on. Second rule, log AX negative log AY is equal to log AX over Y. Similarly, this is regarded as P while this is regarded as Q. So on the left hand side we have P negative Q, while on the right hand side we have X over Y, log AX over Y, which is this over this, A power P divided by A power Q. This is equal to log A base A, this over this is equal to A power P negative Q. Okay, and hence A power what equal to this? The answer is P negative Q. Okay. Moving on, rule number 3. log AX could be written as log base PX over log base PA. Okay, this is the equation of log that switches or helps switch the base of the original equation or original expression. Okay, with the condition that P has to be positive as well as can't be equal to 1. Okay, please recall the following initial constraint. So the proof is as the following: log Px could be regarded as m, while log Pa could be regarded as n. Okay, the following equation could be rewritten as P power m equal to x, while the second one is P power n is equal to a. So the left hand side will be equal to log a is now equal to P power n, therefore this can be written as P power n, while x here is equal to P power m. Okay, what does this simply mean? P power n to the power of what is equal to P power m. So this question mark could be replaced by m over n. Remember from the lesson in the indices chapter. Okay, and therefore this is equal to m over n, which is equal to this. M itself is log base Px, while n itself is log base Pa. Okay, this is log Ax. So therefore the third rule has been verified. Alright, rule number 4. Log a power n x power m could be written as m over n times log ax. To verify this, we need to prove these two equations separately. The first is log a power n x, which is equal to 1 over n times log ax, and the second one log ax power m, which is equal to m times log ax here. Okay, once we successfully prove these two, then we have automatically verified this above equation. Let's start off with the definition of log ax, or we just define log ax as p. This is, and this is leading to a power p equals to x, a power p power gain of 1 over p is equal to x power 1 over p. This is leading to a, on the right hand side we have x power 1 over p. Okay, next let's evaluate the expression on the left hand side, which is log a power n x, and it could be written as x power 1 over p power gain of n x. This is equal to log x power n over p x. What does this exactly mean? X power n over p power what is equal to x? We all know the answer, that it has to be the reciprocal of this, which is p over n. And therefore this will be equal to p over n, and p itself was defined as log ax. Therefore this is equal to 1 over n times log ax. There we go, we have proved this one. Okay, the second one, log ax Similarly, we will also define log ax as a p here, and a power p is equal to x. Likewise, we will evaluate the left hand side, log a x power m, which can be written as log a x power m, this to the power of m. So a power p power m. We simply substitute this x by a power p, which is equal to log base a power p times m. The power to the power, again, we need to multiply the power. Okay, going back to the original definition of log a power pm. A power what is equal to a power pm? The term that substitutes this question mark is p times m. So this will be equal to p times m, while p itself is defined as log ax. So we have got m times log ax. Therefore, we have verified that this log ax power m is equal to this one. Okay, then we have verified this as well as this one, and therefore the above equation has also been automatically verified. Yeah. Rule number 5. A to the power of log ax is equal to x. To verify this or to prove this, we can assign log base a to both sides. Okay, now according to rule number 4, log ax power m could be written as m times log base ax. This power will go down. Similarly, this power will also go down, causing this equation on the left hand side to be log ax multiplied by log aa, while on the right hand side we have log ax. This log aa itself is equal to 1, and we have verified rule number 5. Okay, those are the entire fundamental rules of logarithm. If you see any resource stating the number of rules beyond 5, then some of those additional rules are possibly derived from the existing rules. Okay, so next we are going to discuss the graph of log function. Okay, next we are continuing to the graph of logarithm. The equation we are discussing here is in the form of y equals to log ax. Okay, recall that there are initial constraints in which a has to be positive, x has to be positive as well, and a can't be equal to 1. Okay, log itself is a slowly increasing function. I'm going to give you the illustration. We will pick up random number for both a and x. Log 2 is equal to 1. Log 4 is equal to 2. Log 8 is equal to 3. Log 16 is equal to 4. So as you can see that the higher the value of x, the higher the value of y. However, this y value is increasing slower than the x value. Okay. As such, the graph of the log function generally would look like this. Yeah, it's a slowly increasing function, and this coordinate right here is called the X-Intercept. X-Intercept is the point where the graph crosses the x-axis. The coordinate of this is 1, 0. Okay, because log of any base 1 is equal to 0. Which is equivalent to a power 0 is equal to 1. There we go. Now, this line right here is called the vertical asymptote. Okay, what is the definition of vertical asymptote? Is the x value when y is approaching to either positive or negative infinity. In this graph, the y value is approaching to negative infinity, and therefore this x is equal to 0. So we say that the vertical asymptote is x equal to 0. Okay, this x equal to 0 will never be passed by the graph due to the following constraint. X can never be equal to 0. Okay, moving forward, we will also learn some variations of this graph, which has to do with reflection as well as translation. Yeah. The detail of this discussion will be actually discussed in the specific topic called transformation. However, here we will just discuss the graph of y equal to log ax with the negative preceding it, y is equal to log base a negative x, and the last one is log ax positive a number here. So with the negative preceding the original function, this entire graph will be reflected by the x-axis, so that the graph will be like this. And this coordinate of the x-intercept remains unchanged, which is 1, 0. Okay. Now, with the negative preceding this x, this is a reflection of the original graph by the y-axis. The graph of this would look like this. And this coordinate right here is negative 1, 0. Last one, positive b here, has to do with the vertical translation. This positive b will shift the original graph upwards in the amount of b. Okay, you can see that the basic function or basic graph will resemble to the original. I mean, like the new function, the graph of this new equation will resemble to the original function, except everything now is shifted upwards in the amount of b. So this point is no longer 1, 0. That 1, 0 will become here. This is 1, b now, because everything is shifted upwards in the amount of b. Okay. What happened to the negative value of b? Similarly, we just shift the entire graph downwards by b. So this whole original function is shifted downwards by b. Okay. That 1, 0 will be 1, negative b here. So these are the fundamental graph of logarithm each of you needs to be familiar with. I hope that you're enjoying the video and gaining some knowledge. Thank you for watching this video. Please like, comment, and subscribe this channel. Bye bye.